So things got absolutely wild in the last video. I'm going to just give you guys a quick scroll down. Make sure you watch that video. It went on for a while, but I think you guys got the concept about how we are going to find a better pivot by not randomly selecting and instead by actually putting a bit of strategy into dividing our inputs into groups of 5 and then finding the medians those and then finding the median of the median. So we got these lower bounds and these boundaries that we were starting to create in the end of the last video, and we're now going to start and turn those into some actual runtimes. So I'm going to go ahead and get a nice clean slate over here. I just didn't make the last canvas big enough, so I needed to I couldn't continue right off it like I wanted to do, so I made this one a little bit bigger. So if we get crazy, we will have the same one in the next video. Okay, so let's go ahead. So the problem that we will recurse on, will have the size of at most 7/10 of the input size. So that's going to be pretty good, right? That's the worst case is that the problem that we are going to recurse on will at most be 7/10 of the size, which is what we saw in the last video, right? We started to see that in the boundaries. So we're going to write, this is going to be a deterministic algorithm. So let's go ahead and write this out over here. So TNN, it's going to be the runtime. We obviously will have a boundary over here. So this is going to be less than or equal to. We will have that time that we are going to be recursing on, right? We said 7/10 of n is going to be what we're recursing on. And then we are going to have t of n over 5 plus big O of n. So let's go ahead and get a new color and we can mark this up to see what everything is. So let's mark this up. Worst case is that the size of what we're going to be recursing on is going to be 7/10. This over here is for finding the median of the medians. Over here, and then we will have our left set and our right set, and then whichever one is better will be the one that we are going to attack. Now, what if we wanted to put these in similar terms? So we want to go ahead and we're going to multiply the numerator and denominator here to be the same, just for the sake of being easy. So we will have t 7/10 n over here plus t, we'll have 2n over 10 over here. So we just have them over the same denominators like that. Go ahead. So what issue do we have? Now, if you were watching the earlier videos, right, the ones where we were looking for the initial pivot, right, the one we're going to be picking randomly, the problem here is that we have two problems. This does not fit the master's theorem. This does not fit the master's theorem. Right, we know we have that specific, that specific mold that we're looking for the master's theorem, right? And that's what we're going to be using to determine the runtime to see if we're actually saving time by doing this. But we can't do it when we have these two things like this. So how are we going to go about making this a little bit easier? Let's get a new color. We are going to get wild. We cannot directly go with the master's theorem, but we can use the recursive tree method. Use the recursion tree. So let's go ahead and get absolutely crazy right now, and we are going to just draw this out. So we are going to have on top of our tree over here, this is level 0, problem, size, and this is our problem right over here. So how are we going to split this up with those two values that we had over here, right? Well, we see we're clearly going to split this up in two different ways. We are going to split one of them would be split up to do 2 over 10n, which is why we multiplied it to have like the same denominator. And the other one would be 7 over 10n. So two sub-problems of different sizes, right? So the time over here, time here, and then over here, this would be time spent here would be when you add them up. So 2 over 10 plus 7 over 10, it's going to be 9 over 10. It's going to be the amount of time spent over here. Now we're going to go ahead and do one more level of splitting this up. Bear with me and we will tie this all together. So now we are going to go ahead and split this up. This one can either go one or two ways. It could go to the point where you have the 2 over 10 multiplied by 7 over 10. I can do it. Can I fit? I think I can fit it. So this will be 14 over 100. Make this box a little bit bigger so I have a bit more room. This one will be 2 over 10 multiplied by 2 over 10. So we're mapping out all the possible outcomes here. We'll have another one over here. This one will obviously be 7 over 10 multiplied by the two possibilities. This one here will be 64 over 100. And it'll take up all the room here. 7 over 10 times 2 over 10, 14 over 100 right there. So those are the possibilities that we can have. Now, how much time is spent on this level? Well, I don't have enough room to add them up. But if we were to add all of these up, we will have 14 over 100 times 2, obviously, because we have 2 of them, plus we have 64. Well, not how you write 64. There we go. 64 over 100 plus 4 over 100. We add all those up and we will get a value of 81 over 100. What do we know about 81 over 100? Well, it's essentially 9 over 10 squared. So we can kind of see a pattern that's going to be forming, right? We are going to have 9 over 10 to the power of whatever level we are on multiplied by n. So essentially we're seeing that right over here. We can go ahead and write 9 over 10 to the power of L multiplied by n. If you go to the top level that we had over here, time n, if you put, we're on level 0 at the top. So if you had exponent 0 on top of the 9 over 10 fraction, that's going to be 1, and that's how you get the n. Then you have, you keep working your way down, and that's how you see that the pattern is starting to form. So we see this pattern that's starting to form over here, and things are starting to make a bit more sense. Now from here, let's get, what have we not used so far? Whatever, I'm going with green. So now from here, let's try to map this out, right? This is going to be the part that tricks a lot of people up, but we'll just try to keep it nice and simple. So this is supposed to be a triangle. It's clearly not drawn very well. So on the top, we have n, and this part over here, we will have 2 over 10 L, and down here, we will have 7 over 10 L. And it will never go below this point over here, and it will run off rather quickly if it goes over here. Okay, I'm taking a little reset here. I went on a tangent to end off the initial recording, and this is a part that tricks a lot of people. So I want to make sure this is done as clear as possible. So looking at this over here, right? This is, it's going to represent our worst case runtime. We're going to have some of these branches that will be terminating. It's not going to be this slow, but we always need to consider the worst possible case. Now, we want to get to that master's theorem, right? We still want to get to the master's theorem, but we need A, we need B, and we need D. And we need to find the relation between A and B to the power of D. But what was that last part, right? We just need the relation. We don't really need the values of A and the values of B to the power of D. We need the relation. Do we see anywhere where we can see that relation right here? Well, we learned that we know that this over here, this fraction that we have over here, this is A over B to the power of D, right? We've seen this before. That is A over B to the power of D, which means that if this fraction is less than 1, right? We know that 9 over 10 is less than 1. This clearly means that the denominator is bigger than the numerator. Bigger than numerator. Which means that A is less than B to the power of D, which means that the running time that we are looking at over here is going to be big O of n to the power of D, D being 1, big O of n That's the runtime we get. Now this trick is going to work for a lot of different algorithms. We'll see some ones in the next video. We'll do it with merge sort if you want, and we will see a bit more of this strategy that we used over the past 2 videos. So if you guys managed to stay and understand this entire thing, this bunch of crazy stuff we've seen in the last 2 videos, and really good on you. You're really understanding the algorithms, and it's complicated. So this is one of the tough things that we will run into, but hopefully you guys will understand this deterministic solution, and I'll see you in the next video where we'll look at another algorithm.